Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will discuss 4 different strategies to select a beta prior. For the case when we are analyzing data with a binomial likelihood and the parameter of interest is its probability of success. We will implement these strategies for a particular example. Make sense? Okay, let's begin. So, we are going to be talking about this problem. Okay, this is a problem we would like to tackle, and if you take a closer look to that problem, it's an old example, right? We have dealt with this problem before. As you can see, the parameter of interest is a proportion. In this case, it would be the proportion of students that would quit school if tuition were raised 19%. And we're talking about University of Iowa students. Okay? Okay. So, we know that to analyze this parameter, right, that proportion from a Bayesian perspective, we need a couple of main ingredients: likelihood and prior distribution. Let's talk about the likelihood first. Okay. So let's very quickly review how can we construct the likelihood, right? We know that we can think about each individual student as a Bernoulli random variable, right? So let me refer to each of those students as an xi random variable with a Bernoulli distribution. With parameter, our parameter of interest will be pi. A proportion. Okay. So in this case, that pi represents the probability of success for a Bernoulli, right? So where probability that xi equals 1 is pi. Okay, and just very quickly, let me just mention what xi represents. Oops, this is what I want. Xi will be 1 if ith student would quit school if tuition were raised 19%. Okay? And well, xi will be 0 otherwise. Okay? Okay? Okay. So now let's talk about the likelihood for a single observation. For a single observation. So it would be just the probability mass function for a Bernoulli, right? So it would be the probability of observing a particular value for xi given a particular value of our parameter pi. And well, this guy happens to be just pi to the power xi times 1 minus pi to the power of 1 minus xi. Okay? Okay. Now, note that we have potentially more than one observation, and in this case we will have more than one observation. So let's talk about the likelihood for our sample. For a sample, meaning x1, x2, x3, so on, up to xn, right? x1, x2, x3, up to xn. Oops, there we are. Okay. So, if you are taking statistics 260, at some point you guys will talk about the concept of you know, the likelihood of a sample, and the idea is that the likelihood of a sample is just the probability distribution, and in this case it would be the probability density function for the joint probability density function for these guys, right? So since our observations, our xi's, are independent from sta360, we know that the probability density function for a joint, right, in the case of independence, is equal to the product of the marginals, right? So let me just say that. It's just that I want to take this opportunity to to think about the likelihood from that perspective. Okay, but you'll see that we are going to end up with the same kind of model that we discussed before for the likelihood. Okay, so the probability of observing particular values for this sample, right, is going to be, and remember that we talked about the proportionality symbol. Let me use that proportionality symbol here. So it's just proportional to the product of these guys, right? It's proportional to the product of the marginals. So that would be for the first observation. Then we have second observation, and so on. Make sense? Let me write that down like this, times that, times probability density function for the third, and so on, right? And then we have that for the nth observation, right? Make sense? Okay? Okay, now let's do a little bit of algebra. So note that we could rewrite these guys, p to the power xi times pi, sorry, so pi to the power xi, then pi to the power x2, and pi to the power xn, right? we could do a little bit of algebra, and it would be summation of those guys, right? So pi right to the sum of those guys. And then we would have the same for 1 minus pi, right? So doing a little bit of algebra, it would be the same as 1 minus pi to the power 1 minus x1 times 1 minus pi to the power 1 minus x2 times pi to the power, well, 1 minus pi to the power 1 minus xn is going to be the same as n minus the sum of those xi's, right? Make sense? Well, let me write that down here. Let me do this. Okay. And here, instead of the first one only, we're going to have all of them, right? And let me change this one to make it look nicer. Okay, makes sense? So likelihood of our sample is the same as this, the joint probability density function for x1, x2, x3 up to xn. Since the x's are independent, we have the product of the marginals. We're using the proportionality sign, right? And we have this. Now let me make a little change of variables, if you will. Let this, the summation of the xi's, be just equal to y. Okay. So now what we're going to have here is that the likelihood for these guys is the same as just pi to the power y, pi to the power n minus y, right? And we know that the xi's have a Bernoulli random variable, and since they are independent, the distribution of the summation of the xi's, of the sum of the xi's, has a binomial distribution. So we know that y has a binomial distribution with parameters n and pi, and that's what we used before, right? So in this case, I just wanted you to see this, right, from first, well, from the perspective of constructing the likelihood for the sample, doing it from the multiplication of the marginals for the likelihood of each observation. Okay, just I wanted you to have that perspective. But okay, anyway, so our likelihood finally is proportional to the likelihood of our sample is proportional to this, right? Okay, so let me write that down in terms of y. And also at some point, those who are taking statistics 260 will see that the sum of the xi's, which is y, is something called a sufficient statistic for the parameter pi. Okay, anyway, just a few comments for those who are taking that course, sta360. Okay, so our likelihood has a binomial, well, has the same kernel as a binomial, right? Okay, so now let's talk about our prior distribution. That's the other ingredient to do Bayesian statistics, right? So to simplify calculations, we will use a conjugate prior in this case. So let's just say that we are going to be using a conjugate prior. We know that in this case a conjugate prior is a member of the beta distribution family, right? So let me write that down. So the prior for pi, our proportion, is going to be proportional. Okay, let me ignore that constant that makes the expression for the PDF of beta random variable a legit PDF, meaning something that satisfies those two conditions, that 1 is non-negative, and 2, that the integral from 0 to 1 underneath that expression is equal to 1, right? So I'm going to be using the proportionality symbol, and I'm going to be ignoring the constant, okay? But we know that if we have this, the kernel, we call it, right? We are going to end up with the right answer. We have already done the calculations step by step, and we have seen that this kind of shortcut approach works. Okay, so now let's talk about that posterior distribution. So our posterior distribution would be the conditional probability of pi given what we have observed, right? The number of successes in our sample, right? And in this case, since we're interested in the proportion of students who would quit, we define a success as observing a student who would answer yes to that question. Are you would you be willing to quit school if the tuition were raised 19%? If the answer is yes, then that would be considered a success. Okay. Anyway, so we know that. Let me first write this down in terms of words, that our posterior distribution is going to be proportional to the following product: prior times likelihood. We know that we would need to divide by the integral of this product, prior times likelihood, right? But that's why we're using that proportionality sign, and we know that once you find that integral, it's just a constant, so that's why we're using that proportionality symbol. But again, we know that things will end up well. We have already done all the necessary calculations in general step by step, and we have realized, right, since we're talking about a conjugate prior, we know that the posterior distribution will belong to the same family of distributions. So in this case, the posterior distribution will belong to the beta distribution family. Okay, so we can quickly see that, right? If we just do the product, this is your likelihood, this is your prior. So clearly, right, when you do that product between these two guys, right, you end up with pi to the power y plus alpha minus 1, 1 minus pi to the power n plus beta minus y minus 1, right? Okay, so let me write that down here. Plus y. This is going to be n. Oops. This is going to be n plus beta minus y minus 1. Okay, makes sense? So just from seeing that, right, that's the kernel of a beta. Our posterior has a beta distribution with parameters. Alpha is going to be, and we have this notation for the parameter of parameters of our posterior. Alpha star in this case is going to be given by alpha plus y minus 1, and beta star m plus beta minus y minus 1, right? Okay. So now, the main thing that we're going to be doing in this video is, hey, yeah, we know that our conjugate prior is going to be selected from this family, from the beta distribution family. So, how can we select the parameters of alpha and beta, right? That's the main thing. How okay, makes sense? That's the question that we're going to try to answer here. Okay? So, strategy number 1. One way of choosing alpha and beta, and remember that the prior distribution is just reflecting your knowledge or ignorance about your parameter of interest. Okay? Okay. So strategy number 1, you could graph some beta densities until you find one that matches your beliefs. Okay? So graph some beta densities until you find one that matches your beliefs. Make sense? Okay, so to do that, let's use R. So I'm launching R, right? Let me use P instead of pi. So sequence from 0 to 1, we want a distance of 0.01. Yeah, that should be enough. 0.01 between the elements of our sequence. Okay, let me show you what it looks like. So let me show you the first elements of our sequence, right? Okay, by the way, with this command head, you get to see the first 6 elements of vector or even a data frame. Okay, anyway, so now we said that our strategy is making a series of graphs for different options for beta densities, and then choose one that we might like, one that reflects our knowledge about our parameter. Okay, so let me create an object called beta.1.1 because I want to make it very clear that this guy is a beta with alpha equal to 1 and beta equal to 1. So that's why I'm just using this kind of a long name. Okay. Now let me do something here. You could assign things using the equals, right here, equals sign, or you could use this, right, the less than dash, right, so kind of an arrow, right, and again it's just a different symbol to make an assignment in R. Okay, so something that I believe we have used before is this function dbeta. What dbeta does is it evaluates the density function for a beta distribution, okay, for a beta random variable. So we want to evaluate at all these guys in our sequence, our P, right, and first parameter is going to be your alpha, second parameter your beta. Okay, now let me create another one, and I'm going to be calling this guy beta dot 2.2, and as you can imagine, what I mean by that is that alpha equals 2 and beta equals 2 as well. Okay, so now I would like to have these two graphs side by side. Okay, so what I'm going to be doing next is using command this par as in parameter. So what I'm asking R to do here is to create a canvas that it's going to be divided in two sections. Okay, so a canvas with one row and two columns. So once you're done typing that and press enter, you have just this, a white canvas. Okay, so now it's ready. Now let's plot our beta densities. So let's use that built-in function plot. The syntax is first you place the numbers that you want on the horizontal, then the numbers that you want on the vertical axis. Let me add a main title beta 1 1, and let me just tell R that I want a line. Okay, so type equals L. This is an L, not a 1, L. So I want a line. Okay, so there you are. We have our first graph here. And a beta 1 1, guess what? That's a uniform 0 1. Okay, and we talked about this guy when we discussed non-informative priors. Okay, now let's do the other one, the beta 2 2. Okay, so say that after exploring a few, I go, oh, you know, I don't know a lot about this proportion parameter I am interested in. I think I'll go with this one, with a beta 1 1, which is a non-informative prior. Then you could choose this one, alpha equals 1, beta equals 1. If you know, you go, oh, you know, I think that something that would reflect my knowledge about this proportion parameter is that I think that values close to 0.5 should be more likely than more extreme values, you know, values close to 1 or close to 0. I think that these guys, proportions close to 0.5 should be more likely than others. Then maybe this one would work, and then you pick your beta prior to be a beta with alpha equals to 2 and beta equals to 2. Make sense? Okay, so that's strategy number 1. We just graph a few beta densities, and we choose the one that we believe reflects our knowledge about our parameter of interest, our proportion. Okay, so now let's talk about strategy number 2. So something that I would like you to see here is compare your likelihood with your prior. So this guy here is your likelihood, okay? And this guy here is your prior. So note that when you have a prior here, alpha minus 1 is playing the role of y, right? It has the same functional form here, right? So anyway, this guy here, alpha minus 1 would be playing the role of a y, and n minus y is playing the role, well, beta minus 1 is playing the role of n minus y, right? So if you think about your prior in those terms, from that perspective, when you propose a prior, what you're saying is that your prior is carries equivalent information to an observed data set with alpha minus 1 successes and beta minus 1 failures. Make sense? Right? Can you see it when you compare this? That, oh, if I'm using that as a prior, is as if I already had observed a previous data set with alpha minus 1 successes and beta minus 1 failures. Okay? So, here we go. Let me just write that down. Note that a beta with parameters alpha and beta, your prior, is equivalent to the info contained in a previously observed data set with alpha minus 1 successes and beta minus 1 failures. Okay. Now, let's see. I think I have here something that could illustrate what we mean. Give me just a sec. Okay, so if we go to our lecture notes, right, there what we have is this, right? You'll see that slide. Remember that we're interested in this proportion for the proportion of students who would quit if tuition were raised 19% for University of Iowa students. But say that something similar was done for another university, in this case the Iowa State University. So and you go, okay, maybe that information is useful, right? So in that case, they have information about a sample of size 50 where 10 students would quit school and 40 students wouldn't, right? So similar situation, different university, right? Okay, so note that using that strategy number 2, right, that would suggest this, right? Example. Okay, so alpha minus 1 is the number of successes. So for that particular sample it was 10 successes, and since n was 50, remember, n was 50, the number of failures is just, 40, right? That's what they observed. But then that implies that alpha is 11, right? And that implies that beta is 41. Make sense? Okay, so now just to have an idea of what we mean, let's create beta 1141. Say that we were willing to consider that as a possibility. Hey, using that strategy, I know that proposing a beta with parameters alpha and beta is the same as, I have observed a previous sample, a prior sample, right? Well, not prior sample, because prior is before observing data, but anyway, when you are considering a prior distribution with parameters alpha and beta, is as if you had observed a data set with alpha minus 1 successes and beta minus 1 failures. Okay, so now let's make a graph of this new potential prior distribution. Okay, so for instance, in this case, right, what we're saying is that we are more we are more inclined to believe that that proportion should be close to 20%, and that big values here are not very likely, right? Make sense? Okay, so let's talk about strategy number 3. Okay, so strategy number 3, it's kind of a modification of strategy number 2. What we are going to be doing in strategy number 3 is the following. 1, we will take into account that if you're proposing a prior with a beta distribution and parameters alpha and beta, deep down you're saying that what you had is a sample with alpha minus 1 successes and beta minus 1 failures, right? So since the sum of successes and failures gives you n, the number of trials, right? If you add them up, right, so that would be kind of like a prior sample size. Make sense? Okay, and the other thing that you're going to be using for strategy number 3 is you have a target, a desired mean, okay, and we know that the mean for a beta distribution is alpha divided by alpha plus beta. So you combine those two facts. Okay, one, a desired mean, and again we know this from sta360 that the mean, the expected value for a beta with parameters alpha and beta is alpha plus beta. So this is number one. That's what you're going to be using. And number two, desired sample, well, prior sample size. And again, what we're doing here is just, hey, if alpha minus 1 in my prior is like the number of successes, and beta minus 1 is like the number of failures, then when you do the sum is alpha plus beta minus 2, right? So now let me get rid of this and let me write that down just like that. Alpha plus beta minus 2. And that would be our second condition, if you will. Let me, yeah. Okay. Make sense? So basically what we're saying here is that your knowledge about pi, your parameter of interest, is worth the same as observing a previous sample with you know, this kind of size, alpha plus beta minus 2, which is, again, you're just combining this observation, but we're adding this. Now I want also a desired expected value, a desired mean for that beta distribution. Okay, so example. So say that we want a prior mean of 0.2, okay? And let's talk about one option. Say something like this, okay? Alpha divided by alpha plus beta. As I said, say that we have, say that we wanted prior mean of 0.2, right? So that's the same as 1 over 5, right? So that's 1. And say that you know, I want something like this. Say that I'm willing to consider that my prior knowledge about pi is worth, say, 23 observations. Make sense? Okay. So what we have to do is we just solve for alpha and beta, right? So first, from 2, right? From 2, what we have is that alpha plus beta equals 25. Agreed? Yeah? Because we have a plus here, and then that's 25. Make sense? Then let's substitute that here. Okay? Then, using 1, what we have is, let me copy and paste that. And solving for alpha, what we have is that 5 times alpha equals 25. So in the end, what we will have is that alpha equals 5, right? Okay, so 5 times alpha equals 25. Then alpha equals 5. And then here, right, that implies that beta equals 10, right? Since alpha plus beta equals 25, then beta will be just 20, right? Make sense? So that's how we obtained our potential prior, right? Because what we said is, I think that the beta that reflects my knowledge about the proportion I'm interested in is, I want a beta with this mean 0.2, and I think that my prior knowledge about that parameter is worth 23 observations. Okay, makes sense? And we just solved for alpha and beta. Let's make a graph of that guy. Let's call this guy, 520, beta 520. Let's make that graph for that guy. Okay, so it looks similar to the other one, but the variability, the spread is going to be slightly different because alpha and beta are different. Make sense? Okay, so that would be strategy number 3. Finally, choosing strategy number 4. So the idea is to choose values of alpha and beta that produce a prior probability interval that reflects your beliefs about pi, parameter of interest. And I think that what I need, give me just a sec so I can find it, right, in our lecture notes, what I want to use here. Just give me a sec. So, I found it, but just let me say what we want to do here for strategy number 4. We said choose values of alpha and beta alpha and beta that produce prior probability intervals or interval that reflects your beliefs about your parameter of interest pi. Okay, so let me show you a few choices here. So for instance, let's try with this interval. Okay, in this case, right, we're using that function, that built-in function in R called QBeta. That is going to help you to find quantiles from a beta distribution, right, from a random variable that has a beta distribution kind of behavior, And the syntax is this. QBeta needs you to give it the following information: the probability that you want to its left, okay, and the parameters alpha and beta. Okay, so let me copy paste this one here. This is just going to give you one number. Okay, make sense? Now this guy here is a quantile from a beta distribution with parameters alpha equals 10 and beta equals 40, right? But with 97.7% of the observations to its left. Okay, so that's the second number that you have here. Okay, but if you have 2.5% to the left of this guy and 97.5% to the left of this guy, between them you have 95% of the observations, right? So that's a 95% probability interval. Okay, so now let's copy paste the entire line. Let's retype the name of the object we just created. Right? It's just those two guys, those two quantiles, those two numbers. Okay? So say that you go, oh yeah, I think that with 95% probability, pi should be between 10 and 32%. Well, then a beta prior with alpha equals 10 and beta equals 40 would work for you, right? Let me just show you a couple options more. So this is again a 95% probability interval, but this one is for beta with parameters 5 and 20. Alpha equals 5, beta equals 20, right? So in that case, when you use that beta prior, then what you're saying is that with 95% probability, your proportion is between 7% and 37%. So note that in this case, right, you're more uncertain about your proportion, right, because it has more variability. This interval is wider. Make sense? Okay, one more. We're doing something like that. Again, we're finding a 95% probability interval for a beta distribution with alpha equals 2.5 and beta 10. That's even wider than the one we had previously, right? And in this case, we're saying, you know, I think that with 95% probability, that proportion, that pi, must be between 3.8 and 45.1%. Okay, so if you think that interval reflects what you are willing to believe about your proportion, that's your guy. A beta with alpha equals 2.5 and beta equals 10. Okay, so that's it. So let's summarize what we did today, right? So what we talked about today is we wanted to analyze data with binomial likelihood, and our parameter of interest was pi, a proportion, right? So we're using a conjugate prior, and since it's a conjugate prior, we know that the posterior distribution will be also beta distributed, right? But the point here is, how can we select those parameters for our prior? How can we select alpha and beta? And we have 4 different strategies. One, we could graph a bunch of different beta distributions, beta densities, and then we choose one that reflects what we think we know or don't know about our parameter of interest, right? A second one, we make the observation that, guess what? If you're using a beta prior with parameters alpha and beta, what you're saying is that it's equivalent to observing alpha minus 1 successes and beta minus 1 failures, right? And then you use that to guide your selection. Strategy number 3. It's a modification of that observation. We go, if alpha minus 1 represents your successes and beta minus 1 represents your failures, then the sum gives you the sample size, right? So what we go is, so if you use a beta prior with parameters alpha and beta, is as if you had observed a sample of size alpha minus 1 plus beta minus 1, which is the same as alpha plus beta minus 2. Yeah, okay. Let me use that in combination with the fact that I want a particular value for the mean of my prior, right? And then using these two equations, we solve for alpha and beta, okay? Finally, we could construct probability intervals for a series of different beta priors and just select the one that reflects our uncertainty about the parameter best. Okay? Well, that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.